Welcome to Petrochronics, a research group and extension on petrochronology and its geodynamic implications.
We are a group based in Brazil that also has an international network of collaborators. They presently reside in Brazil, Australia, Finland, Germany, Italy, Switzerland, and the US.
Petrochronology involves several areas of the geological knowledge. We seek to disseminate it in a judicious, yet clear and accessible manner.
In our researches, we use macro and microscopic observations, combining fieldwork, detailed petrography, thermodynamic modeling, processes dating, geochemical characterization, and much more.
From the natural record, we seek to characterize and quantify petrological processes in representative samples, generating comprehensive datasets that are interpreted considering the geodynamic processes that govern the Earth system.
We want to share research, from the basic concepts to the state of the art, promoting courses, spreading work results, and providing collaborations between institutions and people.
We understand that open science is vital to take down barriers to knowledge, and we prioritize the collaborative and open nature of our research. We also propose discussions on integrity and responsibility in the scientific environment.
As values, we believe in diversity, representativeness, and access to information. We seek to mirror these values in our initiatives.
On the YouTube channel, we promote the PTT Talk series, which are presentations on methodologies and advances in cutting-edge research with petrochronology.
Our actions also include the organization of lectures, courses, workshops, and meetings open to the community.
On Instagram and Twitter, we share, on Tuesdays, photos of outcrops and rocks in the field, illustrating geodynamic processes.
And, on Thursdays, photos of thin sections with microscopic features with interesting minerals and textures, reflecting different reactions and petrological processes.
So, if you work with petrochronology or are interested in related topics, be sure to follow us and get in touch. We want our community to grow even more. See you!
So, hello everybody, welcome to our 34th PTT Talk. Today we have the pleasure to have here Aratz Beranoaguirre, and we are the team who hosts this talk with him. So, I am Catarina da Paz, a master's student at the University of São Paulo, and I'm here with Goethe, who is a PhD student at the Federal University of Minas Gerais, with Ciro, who is a professor at the Federal University of Vales do Jequitinhonha and Mucuri, and with Maria Eugênia, who is a professor of the Federal University of Ouro Preto. So thank you, Aratz, for accepting our invitation to be here. And now I will pass it over to Ciro, who will introduce to the Petrochronics and the PTT Talk. Oh, I think we have a problem with the audio, Ciro.
Yeah.
Now we can hear. Yes.
So that's okay?
Yes, perfect.
Okay, sorry. Hello everyone and welcome to the Petrochronics Research Group channel. For those who don't know us yet, the Petrochronics is a Brazilian initiative with an international network of collaborators, especially from the US, Australia, Italy, Germany, Switzerland, and Finland. Our main goal is to explore petrochronology and its power to reveal the geodynamics evolution of our planet. We organize courses, lectures, talks to share knowledge, promote geoscience, and build connections among researchers working in petrochronology, geodynamics, and related fields. So if you are interested in these topics, make sure to subscribe in our YouTube channel and turn on the notifications to don't miss the new videos. Besides, you can follow us on Instagram and on X and stay updated to our last activities. Here in our channel, we host the PTT Talk series, a collection of presentations and discussions about new methods and advances in petrochronology, featuring guests from around the world. Today, as part of the 2025 season, we are very happy to welcome Dr. Aratz Beranoaguirre. Sorry about the pronunciation. So thank you so much for joining us today, Dr. Aratz. And now it's time to Goethe to give a short introduction of the speaker. Go ahead, Goethe.
Hello, everyone. Thanks, Aratz, for joining us. This is the last PTT Talks of the 2025 series, so we're really excited to have you with us, talking a bit about your educational and professional background. Dr. Aratz completed his studies at the University of the Basque Country, finishing his bachelor's degree in 2008. He then moved to the University of Granada for a master's focused on phase equilibrium modeling. After earning this master's degree, he returned to the Basque Country to begin his PhD, and then shifted toward geochronology and working in Luft-Test-Hafnil and rubidium transfer systems for isotope dissolution, alongside some early laser ablation work. Following the first 4 years there, and before formally receiving his PhD, he joined the Spanish Geological Survey in Madrid, and then carried out uranium lead dating by IDTMS. He obtained his PhD in 2016, and in 2019 he moved to Germany, where he has continued working in uranium lead geochronology by laser ablation in the labs of Frankfurt and Karlsruhe. And for the past years, again, he's back in Frankfurt and has been working there. Now I'll pass to Dr. Maria Eugenia to introduce our talk of the day.
So hello, everyone. I would like to start by thanking Petrochronics for the invitation to be here today. It's a great pleasure for me to introduce Aratz's talk. Today, he's presenting a special session on U-Pb geochronology of garnet. Garnet U-Pb dating is a rapidly developing technique with huge potential for understand geodynamic process, especially those in the crust and mantle. However, it also comes with major analytical challenges, mainly because garnet typically contains very low uranium and often hosts a large number of inclusions. So Aratz is gonna walk us into the current state of the method, the main obstacles, limitations, and solutions, as well as the perspectives shaping this fast-growing field, which is especially relevant for a petrochronology-focused audience like this one here today. So, Aratz, thank you so much. The floor is yours.
So, yeah, thanks a lot for the invitation. It's my pleasure. I already knew Petrochronics from some, maybe when you started a couple of years ago. So it's really my pleasure to be invited here. So yeah, and then I just reading the comments now in the chat, I realized that I completely forgot the time difference, that it's so bon dia. Good morning, everyone. I was completely thinking in other things, and I didn't realize that, that's right, in Brazil it's just 9 a.m. And yeah, I will be probably the first one in the world saying, because after Goethe said that it's the last talk of the year, so I would say then Happy New Year to everyone, even if we are in November, but I will take advantage of that. And so then, yeah, I will share my screen, right? Oh,
So I wish you a great presentation, Aratz.
Yeah, can I directly share or how?
Yes, try to share now.
Okay. Then there we go.
Let's see. Wait. Oh.
Yeah, tell me when it's I'm sharing, I think, as we have done before.
Oh, wait. Yeah, I think. Wait. Yeah, now you can try to move the slides, and I think it's gonna work.
Yeah,
yes,
right?
Perfect. Yes.
Okay, so then welcome everyone. I hope you enjoy the next few minutes. So yeah, I will talk about the random geochronology of garnet that we are working on in Frankfurt. There are also many other universities that they are also doing some nice job, but they think we are the best. So I hope this is why you invited me. So this is not, of course, it's not only my job. It's I'm just one member of the group, and which is of course important. No discussing. I think I wanted to put this in the first slide and not in the last slide, because definitely the guys in the picture, we are the fierce members, as well as other colleagues that they have sent us samples, and along with fruitful discussions, made us to learn a lot, and we still are learning a lot. I mean, if I could have done this talk 2, 3, 4 years ago, it would have been completely different. And definitely, I mean, we are at the beginning of this technique, so we are really learning very fast. And if I look backwards, what we knew 2, 3 years ago, it's almost I can consider it almost rubbish nowadays. So I would like to also start with a brief history of uranium-lead geochronology, right? Before the 20th century, of course, you may know that the age of the Earth was, or the knowledge of the age of the Earth was basically linked with the religion. That's why the first estimations were just a couple of thousands of years, where the Jesus Christ born, and blah blah blah. But luckily, in the late 19th century, there were some smart guys, these well-known names, very famous names. This Henry Becquerel, Pierre and Marie Curie, Ernst Rutherford, that they discovered the radioactivity, and they found that in fact uranium and thorium, for example, they decayed. At the beginning of the 20th century, this idea started to really develop. And a lot of motivated people, they start to work on that. And actually, at the very beginning of the century, there was the first uranium-lead dating paper by Beltram Woolwood. I think it was 1910, I think it is. But well, anyway, it was at the very beginning. And subsequently, there was a huge development in the techniques, spectrometer, also this separation, enrichment isotopes, that led already at the mid of the century. They already have quite a good idea about the age of the Earth, right? This Patterson age, or Patterson paper 4.48 is not far away from what we know nowadays, or what we believe nowadays. Let's see, maybe in another 50 years if we still think the same. But well, then of course with isotope dilution techniques, with the spikes, with these isotope traces enriched in specific isotopes, that was like a boom. The people start really working and developing and improving the ID-TIMS techniques, and by the 80s or 90s, we already started with the in situ techniques. Basically in zircon, of course, that it's the mineral that contains, well, not the most uranium, but it's maybe the most common mineral. As we will be talking about garnet, I would like to add also those two papers. This is in 1999, 89, sorry. Klaus Metzger published a paper about uranium dating garnet by teams, although they were not very convinced about if what they were dating was the garnet or the inclusions. But well, and then just a few years ago, in 2019, there was this kickoff of this paper that was really the kickoff of laser-ablation geochronology of garnet. Why do we use uranium lead? Well, I guess you all are minimum master's level, so I guess I will go relatively quick in this part, because you know that the uranium and lead they have a completely different behavior, so they are highly fractionated in a different reservoir. So we will have some minerals or some reservoirs with a high amount of uranium and almost no lead or very low lead, while other minerals will incorporate the lead. Likewise, we have uranium. It's very particular element because it has two isotopes, 238 and 235, that they are decaying in two different lead isotopes at very different rates. Besides, uranium lead, along with other isotope systems, allow us to date a wide range of mineral with very different closure temperatures. And usually the people doesn't comment that also the decay of uranium is the best known constant. The uranium has the best defined or the best known decay constant. Traditionally, we were analyzing minerals that they contain high uranium and high Nu. You see my mouse, right? If I move it.
Yes, we can see it. Yes. Yes.
Okay, perfect.
Mm-hmm.
So we were measuring minerals with this high Nu, this 238 divided by the ratio 238 to 204. So those minerals, I'm sure that you have heard about them: the zircon, titanite, monazite, and rutile. Those, they are benefited by this. They are plotted in this Weatherall diagram, as I told you before. The uranium has two different decay chains with a different speed. But eventually, if there's any reset, any lead loss, any inherited cores, if the system is ideal, let's say, they will plot in this concordia line, because we will have the 207-235 ratio will be in concordance with this 206-238 ratio. However, nowadays, with the advances in the not really in the techniques, because we always usually say techniques, but more than techniques, it's our motivation, or how we have pushed the techniques. We are able to also date or analyze minerals that they fall in this bottom right part of the diagram with this low Nu and low uranium amounts. That they are basically carbonates and garnet. Also, some other minerals. Those, unfortunately, those minerals usually they contain a variable amount of common lead, so initial lead. So I told you before that even if they are highly fractionated in different reservoirs, that's the ideal case. But in those low uranium and low Nu minerals, they usually contain also this. Let's say that this fractionation is not perfect, so the mineral has variable amounts of common lead, of initial lead. If everything is ideal and everything is in equilibrium, those spots will fall, defining a regression line with some domains of the mineral, the garnet in that case, with higher common lead, some others with more radiogenic lead, and eventually they will define a regression line. And with this regression line, we will be able to calculate the age. This works as follows. So imagine we have a reservoir, a rock, where we have at the T0, at the starting point, we should have a constant 207-206 ratio. But let's imagine domains with a different amount of uranium and lead. This heterogeneity is in the crystal. Then, as the time goes on, the domains with a higher uranium quantity, they will produce more 206, so the y-axis will start dropping. So after 1 million years, 10, 50, 100 million years. So by the way, sorry, the age is defined by the where the regression line cuts the Concordia age. How can we do the dose analysis? So basically, there are three types of instruments: the thermal ionization mass spectrometer, the secondary ion mass spectrometer, and the laser-ablation ICPMS. Each of them have pros and cons. Maybe the main pro for the teams is the precision. There are things that you can definitely not do, or not, depending what's your geological problem you want to solve. Maybe the laser or the SIMS is definitely not a good idea. But of course, it's really tedious and long-lasting process to prepare the samples. And also, of course, there is a big difference in price. If we are talking about, for example, zircons, we are talking about 3,000 euros per sample, while in our case, well, it's not 800. This is not updated. It's around 1,000 per day. 1,000 in one day we can do, well, depending. If we are talking about, for example, granites, easy, just single age, we can do maybe 20 samples per day. Again, depending on, you need to keep in mind what's your goal, what's the precision you need to solve your problem. Today we will be mainly focused in the laser ablation, or mainly no, only focused in laser ablation. And the main disadvantage is the need of reference materials for corrections. Well, in case you are not familiar with the laser, that's a sketch, basically a sketch of the system, how it works. So we have the sample cell, well, where we will directly ablate. That's how it looks like. We have the thin sections, and we directly ablate in the thin section. Then with a carrier gas, usually helium, we bring it to the plasma itself. We are 10,000 Kelvin. So in principle, we ionize all the periodic table, but not all the periodic table, almost. Then these ions will go through the mass spectrometer to the detectors, and well, depending on the mass filter, which is the base of the spectrometer, we can have basically three types of mass spectrometers. There are also different lasers, but maybe the difference comes more from the spectrometer side. So depending on the system to filter the mass, so let's say in the mass filter, we will define which elements will go through all the path to the detector and which not. So depending how the mass filter is the system, we will have basically three types of instruments, which is the quadrupole, where we have 4 metal bars, let's say, and then depending on the electrostatic field, only certain elements will reach the detector. in the case of the sector field instrument, it works with a magnetic sector. This is a sector field. Both are sector field. In this case, in the bottom left, we have just a single collector, only one collector, while this on the right side we have a multi-collector where we are collecting up to, well, now it's more with a new instrument, so but let's say 10, 15 different elements at the same time, or isotopes, sorry. The same, it can be the same element but different isotope. The main difference on the between those instruments is the sensitivity. So from the quadrupole to the multi-collector, we can have a huge difference in the sensitivity, which in the case of the uranium-lead dating of garnet, as Maria have said in the presentation, we definitely need to go to the most sensitive instruments because the uranium, it's really, really low. Yeah, sorry. So this is a picture of our lab in Frankfurt. So we have the laser ablation system. It's an excimer laser, 193 nanometers. And we can work either with a single collector here on the right, or in the multi-collector. It depends a little bit on the samples. So we use for the laser. The good point is that for us, there's no special sample preparation beyond the normal petrographic work. So you need to know what do you want. You need to know how your sample look like. So it's not just do the thin section and bring it directly. I mean, you need to work, but well, this you should do it with in any case with your samples, no? So that's no. We can work either with thin sections or with mounts, with separate. Those are garnets from skarn. So you can also, it's a big crystal, so you can separate them and mount them in epoxy, and we can easily analyze. Actually, now this is a little bit old-fashioned holder, because nowadays, since a couple of months, we have we can do even 9 thin section. We have a new holder where we can fit 9 thin section. And yeah, that's also in the case of the garnet. Usually we go around 10, 20 microns deep. So it's also regular thin section work. I mean, we don't need any special preparation, as I told you before. With a regular 30 microns thin section, it's enough. And also here on the left side, you can see the different spot sizes we can use in our laser, depending, of course. Well, I will talk about that a little bit later. So one of the first problems we face when we work with laser ablation is the fractionation. In that case, we have 2 types of fractionation that we need to correct for. On the one side, we have this leaf, that's the laser-induced elemental fractionation, and the PIF, or PF, it's the plasma-induced one. So in the leaf, we need to basically correct for the downhole fractionation. Although we know that this melting, condensation, and plasma plume, we need to control them. So we need to really have control about the energy we are ablating with. And then the ablation, the downhole fractionation, we must correct for it. We will see it in the next slide. Likewise, we can have some trouble in the plasma, depending on the plasma loading and some ionization efficiency, etc. But the most important is the inter-element fractionation, that we will see it also in the next slides. So as I told you, one of the fractionations we have is this laser-induced elemental fractionation, and then that comes, you can see it in this graph from Ingo Horn in the 2000s. So the idea is, it's let's make it quite easy to understand. Let's make it basic. As soon as we go deeper in a hole, as soon as we are ablating, the 238 is heavier, so it's more difficult to remove or to bring it out from the hole and bring it with the gas to the laser. So that means that the 206-238 ratio, as the 238 is becoming less and less abundant, we will have it. It will increase during the ablation. So we need to correct to find the initial value. That will be the real, our initial measured value. And then we need to correct for this instrumental mass bias, that's the plasma induced, because during the whole session that can last 12 hours or more, there can be differences in the uncorrected ratios. So here on the right side, this is the program we use in Frankfurt. And you can see how the 638 increases with the time. And that's what we need to correct for. And this is the yellow part is the corrected one. The 207 to 206, they have very similar, almost the same atomic weight. So it's almost it's close to zero, but not close. I mean, we also correct for it. Likewise, as I told you, we have this plasma-induced fractionation, that's the drift over time instrument that we need to correct for. This can come from slightly differences in gas flows, also the temperature in the lab. When there's people around, we can have slightly differences in the lab temperature. That this is also affecting the detector. Usually by night, there's no one here. We have temperature detectors in the lab, so we see that there are a couple of 0.1, 0.2 degrees less. So it's slightly colder during night. So we need to correct for it. This is the 238 to 206 238 or the lead. For doing so, usually we use the NIST classes because they are homogeneous. So we use them for correcting the true value of the lead correction, and also for correcting the lead uranium ratio during the overtime. Apart from that, we need the garnet reference materials in the case of garnet, because we need to account for the different behavior between the NIST glass, which is silicate glass, but it's artificial glass, and the garnet. This is an example. This is a garnet example where we have 140 million years age before correction, and we make it after correction, after using a matrix match standard, that it's another final correction in the lead to uranium ratio. We go 10 million years older. Okay, that's already like 6-7%. So imagine if you go, for example, in the rocks you have in Brazil, that you have from 600 up to 2 billion or even older. In the San Francisco is, this craton in Brazil. Imagine 7% in 2 billion is quite a big offset. Those are the garnet reference materials that they are published so far. If you have a quick look, you will realize automatically that all the analyses are done, all the standards are for grossular andradite type of garnet. So this is still some work in progress in different labs, because we are still in a need of pyropalmandine type, garnet type of reference materials. So let's go let's leave aside the instrumental part and let's start with the garnet. So the garnet, we know it's this cubic nesosilicate where the divalent ions go in the dodecahedral side. Magnesium, iron, manganese, calcium, the most common ones. And also we have these trivalent ions. They go in the octahedral position: aluminium, ferric iron, chromium. we know that the most common garnet series are this pyropalmandine spessartine, where we have the aluminium in the octahedral side, or even they can have a little bit different proportions of grossular. And on the other hand, we have this basically grossular andradite with eventually with chromium with uvarovite, where the main component is the calcium in the dodecahedral side. However, nowadays we know that the garnet is not only those end members, but it's a supergroup where we have more than 30 different end members. You have all these weird names that maybe you have never heard before. It was defined by Ed Grew 10 years ago. And the interesting point is that here we already see that there are some end members that contain quite a lot of uranium, up to almost 30% of uranium, right? This elbrusite, kimseyite, or schorlomite. Actually, this is a master work of a master student in Frankfurt, where he did some uranium mapping in some garnets, and we can see that definitely the garnet is incorporated in the uranium is incorporated in the garnet, because it's also following the zonations. And if you see it in this left-hand side example, we can even see that there are some crystallographic phases that they are more prone to uptake the uranium, right? And in that case, for example, it's up to 7 ppm, so 8 ppm of uranium, also in the case of Mali. This is, by the way, this is one of the most used standards or reference materials, this Mali, that was from the paper of Seaman et al. 2017. So those guys, this Deng et al., these Chinese authors, they did a couple of years ago a compilation of uranium concentration in garnet, and they already saw that there were like two groups. On the one side, we have the garnet with a high concentration. They put the limit in 2 ppm, so I would even put it a little bit lower. But anyway, we have this skarn garnet or alkaline rocks with uranium contents that they can go up to 100 ppms, so as much as a zircon. But what you probably, as a Petrochronics group, what you are probably more interested is this left side of the graph, where we have all these eclogites, all the metamorphic sensulato garnet, where the uranium concentrations are really, really low, definitely below 1 ppm, but here we are about below even 100 ppbs. No, and that's really what makes the analysis challenging. Oops. Yeah, as I told you, this is just an example that we published a couple of years ago. It's a skarn garnet from the Erzgebirge region. Erzgebirge is in East Germany. It's a historical mining district since the Romans or something like that. It's really, really old, but still there's a lot of research going on. The ore geologists still do a lot of things there. And this is an example, right? We had the garnet samples from different localities and different mineralizations, and we were able to find at least 3 different events with different magmatic pulses that they produce different mineralizations. But what I wanted to emphasize here is that due to the high amount, the success rate in this type of garnet is almost 100%. So almost all the garnet work. So I don't want to go deeper here, because from the analytical perspective, that's what I'm more interested. They are not very challenging. It's just who you analyze they work pretty well. This is also another example from this work of Nico Meyer, where in the same district in Erzgebirge they have some garnet or some tin mineralization, and we found two different types of garnet. On the one side, garnet with very low tin concentration that they gave H's around 320, while the tin mineralization with the garnet containing up to 7% tin, it's definitely a second stage of mineralization around 15-20 million years later. But here, what is really challenging is the metamorphic garnet. They contain very low amount of uranium and therefore a very low success rate. So this is the first paper that was published by my colleagues in Frankfurt, and it's a very interesting paper, by the way. And some of the points that they are covered here, I will show you them in the next slides. So the problems, one of the first problems we found in the garnet, as we are dealing with a very low uranium, is how big can we go in the spot size? No, because one can think, okay, if I have low amount of uranium, if I do bigger spot, I will have more signal. Yeah, but the garnets usually are not. They don't agree with that because in many cases they are cracked, they are broken apart, and it's not easy to set spots in the garnet. So we are a little bit limited, restricted, and that of course makes it challenging to get signal, and well, sometimes we need to really search for the slightly higher uranium domains. And of course, we have the problems of the inclusions, right? In many cases, we have a garnet full of inclusions. This is an example from the Himalayas, where the core of the garnet is definitely full of inclusions. There's nothing to do. We cannot set spots there. But well, in that case, for example, the rims are relatively clean. Also in this other example of the Munchberg Massif, where the rims are relatively clean, or they look relatively clean. That's always not the case anyway, but well, they can be maybe dated, the rims, but definitely not the cores. A couple of months ago, we published this paper where we found that sometimes, even if we are not able to see the zircon inclusions because one can say, okay, this area where I'm showing now with the mouse looks like clean, there's no zircon, we can set spots there. But when then you found that probably they were also affected by zircon or rutile ilmenite inclusions, and in that case, we were obtaining everything was older than expected. But you can see, even if the garnet look relatively, this bell-shaped manganese maps or lutetium also shown perfectly distributed, but look at the titanium, zircon, uranium was really everywhere. We had zircons everywhere that eventually, that even if you cannot see them in the petrographic thin section, definitely they were there. Another problem that we can have when we are dating garnets is that those garnets contain more common lead than uranium, right? So then this type of garnet with high lead and low uranium, they are definitely unsuccessful. We cannot do anything with them. Look at this example, this age, right? It's so we need samples that they have definitely higher uranium lead ratios, as I told you before. So sorry, I was a bit sick the last days. So this is an example how the data may look like. This color code depends on the uranium content. So this light blue, whitish are spots that they contain all very low uranium, while those red ones are rich in uranium. Yeah, well, one can think, right, that maybe there is a regression line here, and also, okay, those samples may be affected by inclusions. They have this red color, so that means that they are rich in uranium. Okay, maybe. So what we do in the MSW is horrible. So in those cases, for example, it's not. I mean, this is quite normal case. And the only thing is now what we need to do is really to go one by one all the spots, see how the time resolve signal is, and see what we can do. If we can really improve that, get an H from the analysis, and that's what I will show you in the next couple of slides. So of course we have those type. No, if we assume that this is our real regression line, we can say, okay, those inclusions they are more or less in the same regression line. So eventually they can be cogenetic. Some others they plot in really like 900 million years, or there's maybe inherited zircons or whatever can be. So let's imagine the first case is cogenetic inclusions. So we will focus now in this spot. No, we have this is a sample we dated after all this data processing, and I will show you because that's a very beautiful example where we have. Forget about this. This comes later when we do all the processing. But imagine we go to this spot, and that's what we see. Right, that's the time resolved signal, that's the background, and that's the signal. Here you clearly see two different domains, right? There is this domain with a high uranium and high lead, while we have another domain, looks more homogeneous, and with higher uranium. So definitely here we have a domain that it's usually inclusion, high can be, I don't know, pyrite or feldspar or whatever. If we separate the two domains, we split this spot in two. We have the garnet, and the inclusion is over there, which in this case it's cogenetic because it falls in the same regression line, right? If you can see, we have the garnet inclusion. For example, the lead is very obvious. We have all together, it's 1.3 ppm of lead. If we separate this, definitely we have something which is rich in lead. Probably I would say it's feldspar, pyrite, or something like that. Of course, we can have the other. On the other hand, we can have non-cogenetic inclusions. That's the case. We have, imagine we do the spots, and when we plot for the first time, we had the ellipses here, and when we separate this first domain, a bit bumpy, ugly, and the second domain that's more homogeneous, we have also, again, two different clear domains. And in that case, we have garnet and an inherited inclusion. Probably zircon, I would say. Can be rutile, but I don't think so. That's probably a zircon, no? That they usually are more refractory. And in that case, for example, we say, right, because you can say, okay, this is an outlier, I'm not considering it. But if you go really inside the time resolve analysis, you can really separate inclusion, you can separate garnet, and get a pretty good H, right? Of course, I mentioned many times during the talk that we are very low in uranium, in metamorphic garnet. Okay, but how low are we, and how low can we go? So imagine when we do a zircon spot, in that case, as an example, this GJ1 reference material, very known, used in many, many labs. Okay, if we do the calculations, how much uranium there is in this spot, in this hole, that means that we calculate that it's 3.5 picograms of uranium are being sent to the spectrometer. So the point is, if we do the same calculation for uranium, can making bigger spots, how low can we go? What's our limit? So far, this is the paper where we got the the lowest uranium contents, and in any way we got reliable H's. Know that there were some samples from the lower crust of the Cabal craton that they were brought up to the surface by kimberlite, and well, they are pretty good. No, for example, here it's all aligned. Even here we were using sillimanite as an anchoring point to make the regression line better defined, so we can have a better better defined regression line, so we will have a smaller uncertainty in the end. So far, the lowest garnet we have done so far, it's those ones here. There are different samples from different people and different localities. And the interesting is that even being at very, very low uranium concentrations, we were able to get reliable H's. No, we went down to picogram level, so it's PPTs. We go back to this slide. Now we calculate that 1 ppb is actually 1 femtogram of uranium, which is around 3,500 times less uranium than in a regular zircon analysis. That's what we are nowadays analyzing, what we are measuring nowadays. That of course improved quite a lot. I showed you before that the success rate in the garnet, in a metamorphic garnet, is around 25-30%. I could say nowadays we are slightly better, maybe 40 up to 50% eventually. So we have improved quite a lot in the last couple of years. And now, to finish, I would like to show you this beautiful example from Steel Rutile in the Alps, in the tower window. This is a work that was done. I don't know if you know it. It's a Pollington and Baxter. They collect those big garnets. Or it's a CS zone cut in a carboniferous granodiorite, and they got those big garnets that they were able to sound and drill. So they were able to date the different zones as if it was this 3-ring style. So they got 12 different garnet zones, and they calculate a growth time of the garnet of 8 million years. So Ethan was kind enough to send us one of those garnet that they collected, and this is actually the map we did here in Frankfurt. We did this 193 spot size, so you can see this is the scale of the spot size we did. And well, we selected 8 different zones for uranium lead dating, to see if we were able to date them, and also to compare with samarium neodymium H's. That's what we obtained also. So we were able also to distinguish core and rim, even if each of the zones are more or less overlapping with the next one, so we cannot really distinguish zone to zone, but it's a clearly junction of the garnet. If we compare it with samarium neodymium H's of this Pollington and Baxter paper, we got a similar trend. Yeah, that's right, that here we have a little bit different, because their older rim was around 20 million years. We have slightly younger, but I'm not sure if it cannot be even that they mixed those two domains. This can be also. But well, in any way, we are quite in agreement with the samarium neodymium H's. So that's clearly showing that the uranium lead H's are also reliable, and we can distinguish core and rim. However, we need to take into account that this core and rim difference, we need so far with the uncertainties we have, we are only able to do it in very young zircon. So imagine in that case we are having for the core, we are having around 5% of uncertainty, 10% of uncertainty for the rim, very young. If we go to a garnet that grow during 10 million years, 11 million years, in the Bariscan, for example, and taking the same uncertainties, we won't be able to distinguish core, right? The uncertainties already overlapped. So for making distinguishable the core and rim, we will need to go to really 1%, 1.5% ages, which is really challenging, but who knows in the future if we will be able to do that. So as summarizing this steel-rutile garnet, we can say that, of course, the garnet growth, it's easier to distinguish in the young samples. It's evident that if the garnet grew during 50 million years, that's unrealistic, but just to go to an extreme, it's easier to distinguish. And of course, the amount of uranium and the amount of lead makes easier to improve the uncertainty, so we can distinguish better. So just to conclude, the uranium-lead garnet is a relatively inexpensive method nowadays. We are about 40%, 50% of the samples work, so we have a quite high success rate. You have to think that when we started like 5, 6, 7 years ago, maybe the success rate was only like 10%. So we have improved quite a lot. We can go really in a low uranium garnet field, and of course, this can make an advance in how we understand the orogens, because we can definitely date the pore-grade metamorphism and also metasomatic events in the mantle. I didn't want to talk, but we have also garnets from the mantle, then pyroxenite, metasomatic garnet. So definitely, it's opening a new window in the metamorphic petrology, right? Of course, it's not everything good. There are also many inclusions that they can make our analysis useless. We have in the very young samples, the 206, 207 lead is very, very low, because of course there's no time for the 235 to decay in enough amount. And the main problem that we are facing now is that there's no official low uranium almandine pyrope reference materials, when the majority of the metamorphic garnet are usually this almandine pyrope series. So thanks for your attention, and and if you have any question, I will be happy to try to answer.
So thank you, Aratz. It was a great talk. Very interesting to see how this technique is improving over the time, and how we are facing with these obstacles of the low uranium and garnet, and with the reference materials. So thank you very much. Now we are open for the question time. So everybody that is attending, feel free to send questions and comments that we are going to start the discussion. To begin, I have 2 questions that I want to ask you. The first one is about diffusion and redistribution of uranium and lead and garnet. Is there a problem with this, considering like a fluid-rich system, a peritectic garnet? Do we have a redistribution of these elements?
Well, first of all, I could say no. I mean, it's not. It's at least something that we haven't really observed, because at least I would say 100% no for uranium, because uranium looks like it's happy in the crystal lattice of the garnet. With the lead can happen. We haven't seen so far, but I would say from the point of view of the theory, yes, definitely we can have. But we haven't observed it so far.
Okay.
But it can happen. I mean, I could say from the theory point of view, definitely, because what we have observed, or what we know so far until now, at least our knowledge, is that the garnet is the lead is not happy in the garnet. So definitely, I could say that if there is a possibility to escape the crystal, the lead will do.
Okay. And the other question is regarding like to separate and split what is microinclusions of zircon or other minerals that we cannot see in imaging. The only way to separate these inclusions is during the reduction of the data, or is it possible before doing the spots and the analysis?
Yeah, that's an interesting question, and I hope if I go very long, you can cut. But yeah, I mean, sometimes definitely we don't see them in the petrographic thin section. But then when we have after our experience doing the time resolve analysis with it, we see really that the garnet that have no inclusions, it's usually flat. The signal of uranium is flat, so they are quite homogeneous in the signal.
Mm-hmm.
And when you have these micro inclusions, because what I show in the two graphs, it's like the most beautiful or most extreme examples that you can really see two domains. I mean, it's easy. But when you have micro inclusions, like in this Oman paper, sometimes it's very bumpy. So it's actually probably more than one inclusion. It's not one inclusion. It's very and sometimes I did I talk about that with Bernardo Cesare, a professor in Padova in Italy, and I talked to him about this problem, and he sent me some garnet. Well, he told me, because he's one of the best petrologists in Europe, in the world, I would say. And he really, in garnet that for me were homogeneous or let's say clean, he told me, no, in this area I see inclusions, in this area I see inclusions that I was not seeing them. And when I was shooting, definitely the clean areas that Bernardo told me they were clean, and the areas that I thought they were clean, but Bernardo told me they are not clean, they were not clean. So maybe if you have a strong experience in petrology, maybe you can see them also.
Okay.
But it's not easy, I could say,
to
distinguish them petrographically. Yeah, and also if they are not in the surface, you cannot even see them with the SEM over there. So you really need to do in the classical microscope and do really spend time and see really where the free domains are.
Okay. So thank you.
Yeah, you're welcome.
So Aratz, I have one question, maybe similar with Katarina questions. Do you think that time of flight, ICP, could be useful for us to trying to date this garnet or not?
The problem is the detection limit. I don't know about which, but I could say that the detection limit of the time of flight is slightly worse.
Yeah, I think it's...
Yeah, that's because, for example, for the scar garnet, we use the single collector. I would say for scar garnets, probably you can do. The problem is the metamorphic garnets. That's the one that have really low uranium and lower lead, because that I should have said in the talk. The problem is not actually the detecting the uranium, but the detecting the lead, because we are measuring basically three elements or three isotopes: the 206, 207 lead, and the 238. The 207 lead is the least abundant of the three. So the problem is this is the main issue, the 207. No, and that's a main issue. I mean, if you go to scar garnet, that they can have up to one. Yeah, it's like a circle.
Yeah, I understand.
So they may be like a circle. Mm-hmm. In terms of concentration. So this shouldn't be a problem. I haven't tried. I would like to try also, for example, in SIMS. I haven't done SIMS, but I would say SIMS. I would say that probably the scar garnet are doable.
I have a quick question. Do you hear me?
Yeah,
Right.
yeah.
Okay. Have you tried to date the manganese-rich variety of garnet, like spessartine?
Yeah, but not successfully.
Why?
But not many. No. I think it's just we were unlucky with the sample. I don't think it's nothing to do with the manganese. We haven't tried many samples.
Okay.
But in principle, I would say that it's not definitely anything you can do. I mean, it's just that we have done. I don't know, 5 times, 5 different samples, and they didn't work. But I would not say that it's not possible. It's just we were unlucky with this specific sample.
Yeah, I'm wondering about the concentration of uranium of this variety of garnet, but I don't know. Maybe it's an issue, maybe not.
Yeah, I don't know. I mean, it's something that we still don't know. I mean, we need time to learn. What is clear is usually you have the problem that, for example, the more mafic rocks, more mafic like eclogite.
Yeah.
Usually they contain less inclusions, but they have no uranium because the rock usually it's very poor in uranium, like a more or whatever. And the more felsic rocks usually have more uranium, but you have more inclusions. So is there a way to know beforehand which sample will work or not? This we have no idea so far. This we don't know yet. I don't know if in some years we continue working on that, we may be able to say something else.
Yeah, thank you.
We also have some questions from the YouTube chat. I'll read one from Matheus Andrade. He has a question about garnet size, and he's asking about if centimetric garnet porphyroblast, uranium lead.
Yeah, well, I mean, this is nothing to do with the size. With the precision, has nothing to do, because it's more the amount of uranium and lead. I mean, you can have here I have a garnet that this is, I don't know, 5, 6, 7 centimeters, has no uranium. So I mean, I can put I don't know, 1 centimeter spot, but there's no uranium in the end. So it's nothing to do the spot size or the garnet size with the uncertainty has nothing to do. It's just the composition or the amount of uranium or the amount of lead.
So we have another question from Lucas. A question about the method. What proxies and or tools are used to prospect good spots other than uranium content? Is it a try and error exploratory work, or analysis with other sensors are made prior?
Yeah, it's completely exploratory. So what we do is we do. So nowadays, how we work is usually we put the samples. Now we can put 9, and we just have tests. We do while we are there in the lab and during the day. We are checking the garnet and also core and rim in different domains, and we do analysis of 1 second, 2 seconds, and we see the signal. We see if they have more uranium or lead. If they have more uranium than lead, that's already promising. So then we set spots and we run the sequence. We do the analysis overnight.
Okay, and we have some
I
comments.
also have a question.
Yeah, go ahead.
Yeah, thanks.
I'm curious about, and you mentioned the idea of, for example, when dating eclogites, that okay, you do not have inclusions, but then you don't have enough uranium as well. And I'm interested in this idea between the compositional differences when we think about metamafic and metasedimentary rocks, how they would influence the lead retention, the robustness of the uranium lead ages. If you have any insights, okay, focus on the metamafic occurrences, focus on the metasedimentary ones, or which metamafic rocks could work better, or something like that.
That's a very easy answer. I have no clue. We have no idea. No idea. I've done garnet in eclogites that the whole rock composition had a little bit more uranium, and they didn't work. Some others that they were extremely poor in uranium, and they work. So I could say. So the problem is, I could say actually the problem is not the amount of uranium in the rock, but the major element composition. In terms of, yeah, okay, you have a little bit of uranium, but where is this uranium going? This depends on the mineralogy you have. And you know, if I have no clue, but I could say that if you have more in an eclogite, if you have more sodium in the CPX, maybe it works in the crystal lattice, takes more uranium or takes less uranium, so this uranium is free. For the garnet, I don't know. I mean, I think there are many variables that it makes it difficult to solve. So we do, but definitely the H's are the same. I mean, we have done H's or analysis in rocks from the same domain and in mafic domains and felsic domains, and the H is the same, or at least unresolvable for us.
Thanks.
Yeah.
Just a quick question about the eclogite.
Wait a second.
From...
I need.
Okay.
I have 10 minutes old. Okay. Sorry. I have.
No problem. About the eclogite from Capricorn, if I'm not wrong, you have date clinopyroxene, garnet, and rutile.
Yeah, but this was not in this talk, eh?
Yeah.
Yeah. I mean, that's what I presented in the Goldsmith. Yeah.
Yeah, that's it. And why garnet and rutile produce a very younger age if we compare to clinopyroxene?
I have no answer yet for that. I have some ideas, but I'm writing the paper now. So I have some ideas, but they're still not clear. I'm still discussing with people. So I'm sorry, but I prefer not to answer these questions. At least
No
not
problem.
in a YouTube channel. Not in a YouTube channel, at least.
Okay, we are waiting for
I mean, I have
this
some ideas.
answer.
If you drop me an email, I can.
Okay, sure.
I can, but yeah, I rather because I'm working on it now, so I prefer not to say it in an open channel.
Okay, good luck for this.
So Mateus, who made the first question, has a comment. I was wondering because some larger garnets tend to grow in slower rates, therefore resulting in a minimization on the age error, but also tends to have diffusion. But if we do not have uranium at all, as the case you showed us, yeah, the measure of the problem. So yeah.
Yeah, the point is because in the case of the Alps, I'm just hypothesizing, but the point is these big garnets are formed in a CS zone, in a melonitic area, so you have water influx continuously. So if you have, like, let's say, uranium supply continuously, of course you can grow the garnet and improve the uncertainty, the result. But again, it depends on the uranium and lead concentration. It's because we do have garnet. maybe we were not able to distinguish coral green, but I do have garnet that they are 100 plus minus 1 or plus minus 0.5. That's the internal uncertainty. Then we need to add the external and the external uncertainty. So the external uncertainty means, so if I do a garnet that it's 100 plus minus 0.5, it's maybe because the garnet has a uranium lead concentrations that allow me to really define perfectly the regression line. But then I need to do the external uncertainty, which is around 2%. So my H will be 100 plus minus 2 minimum. I cannot improve that. And this external uncertainty refers to, let's say, if I do the same garnet in 6 months, which H will I have? So it's when I analyze the standard, the secondary garnet reference materials, I don't have always on spot. I don't have the same H exactly. Sometimes I have 300, sometimes I have 302, sometimes I have 299. So it's a little bit variable, the standards. And this I need to account for it in the final results of the garnet, also of the samples of the unknowns. So it's also sometimes it's not only the problem of the garnet, but it's also the technique.
Yeah, so thank you, Aratz. It's a pleasure to end the PTT Talk series from 2025 with your talk. It was incredible to know more about this U-Pb geochronology in garnets. So thank you again.
Yeah, thanks a lot for the invite. And if someone has any question, you can drop me an email. We'll be happy to answer.
And when you do have new results, we can bring you back again to discuss uranium lead, of other minerals as well. Always welcome to come back and share some knowledge with us.
Yeah, that will be cool. So yes. Have a nice day then.
Thank you. Thank you everyone for joining us as well.
Yeah.
Thank you.
Thank you, Aratz.
Bye-bye.
We see you next year.
Yeah.
Don't forget to like these videos, guys, and share with friends.
Bye.
Bye-bye. Thank you.